Now, we've already discussed how to translate ordinary language statements into propositional logic, and we've discussed how you would go from statements like this by identifying the simple statements that make up the statement, and then identifying the logical operators and turning them into symbols in propositional logic. And now what we're going to concentrate on is how to determine certain properties of statements written in propositional logic, as well as determining the validity of arguments in propositional logic. Okay? Now, the first thing that we want to discuss is actually the idea of truth functions of logical operators. Okay? So now remember we said that logical operators like the negation tilde, the conjunction dot, the disjunction wedge, the conditional horseshoe, and the biconditional triple bar are all truth functions. Okay? What this means is that they tell us how to determine the truth value of the statements that they occur in. And they help us determine the truth value of the statements that they occur in because they themselves have a certain meaning, and those meanings give you rules, in essence, to determine the truth value of those statements. Okay? Now, the meaning of a logical operator is defined by its truth function, okay? And its truth function is best illustrated rather than explained, okay? So here we have the truth function for the negation, and it's given as what is called a truth table. So this is a truth table which shows you all the possible truth values a specific statement can have, okay? It doesn't tell you what the truth value that statement is. It tells you, based on the structure of that statement, what the possible truth values that statement can have given its parts. This is because the meaning of statements in propositional logic are associated with their truth values. So the meaning of a statement in propositional logic is its truth value. Furthermore, we determine its meaning, the truth value of a statement, by the meaning of its component parts. So the meaning of statements in propositional logic are compositional. The meaning of compound statements are dependent on the meaning of its parts. Okay? So here we have the truth function for the negation operator. And this truth function tells us that whenever P, a component part of the negation not P, okay, is true, the negation not P will be false. And whenever P is false, the negation not P is going to be true. So this defines the meaning of the logical operator, okay? I highly recommend that you memorize the meaning of logical operators, okay? The easiest way to memorize the meaning of the negation operator is to simply understand that if P has a certain truth value, then negation P will have the opposite truth value, okay? So here we have an example of a simple statement. Albany is the capital of New York, okay? And we're going to represent this with the propositional variable A. So if Albany is the capital of New York is true, okay, then not A, it is not the case that Albany is the capital of New York, will be false, okay? And this is given to us by the definition of the negation tilde, okay? The truth function of the negation tilde. Whenever A is true, negation tilde will be false. So if A is false, negation tilde will be true, okay? So anytime you have P being true, negation P will be false, and anytime you have P being false, negation P will be true, okay? So next we have the conjunction logical operator, okay? And the truth function of the conjunction logical operator is here on this table, this truth table here. Here you have a statement form for the conjunction, and it's made up of statement variables. So you see here the lowercase p and the lowercase q. They stand for any statement, okay? So you can replace p with any statement, either a simple statement or a compound statement, and you can replace q with a simple statement or a compound statement. And when you do so, you'll end up with a conjunction, okay? Given this form of a statement, you have this truth table which defines the truth function of conjunction, okay? Now, because we have three components here, okay, we have the P, the Q, and the dot logical operator, okay? the truth value of the conjunction P dot Q will depend on those three components, okay? First of all, it will depend on the truth of each statement, okay, P or Q, and then it depends on the meaning of that dot. The meaning of the dot is actually given to you by this truth table, okay? So this truth table tells you that whenever P in this statement here is true and Q in this statement here is true, you'll have the conjunction being true, okay? And whenever you have P being true and Q being false, this conjunction will be false, okay? Also, whenever you have P being false and Q being true, the conjunction will be false. And if you have P being false and Q being false, the conjunction will be false, okay? So these are the possible truth values that a conjunction can have depending on the truth values of its component parts, okay? This also defines the definition for the logical operator dot. The dot tells you, depending on the truth value of its component parts, okay, you will have these truth values for the conjunction, okay? Now here we have the statement, today is Monday, and we have the statement, it is raining outside, and then we have the conjunction of that, today is Monday and it is raining outside, okay? Now, the truth of this conjunction, because of the truth function, okay, depends on the truth of the component parts along with the definition of the conjunctive dot, okay? So if this is true, it's true that today is Monday, and this is true, it is true that it's raining, then the conjunction, today is Monday and it is raining outside, will be true, okay? One way to actually understand or remember the truth function of the conjunctive dot is with a single rule. And that single rule is a conjunction is only true if both conjuncts are true, okay? So notice how the only time that the conjunction is true, okay, is when both P and Q are true, okay? And in all other cases, the conjunction is false. So the one rule that can help you memorize the truth function of the dot conjunction operator is that the conjunction is true only when both, these are called conjuncts, are true, okay? Both of the parts that make up the conjunction are true. Next we have the disjunction, okay? So this is the truth table for the disjunction operator, and this defines basically the truth function of the wedge logical operator, okay? So this tells us that whenever it is the case that the parts of the disjunction have a certain truth value, okay, then the disjunction will have these corresponding truth values, okay? So whenever P and Q are both true, the disjunction will be true. And whenever P is true and Q is false, the disjunction will also be true. And whenever P is false and Q is false, the disjunction will also be true. And whenever P is false and Q is false, the disjunction will be false. The one rule that you can use in order to memorize the truth function of the disjunction wedge is the following. The disjunction is always true unless both its parts are false, okay? So notice how the only time a disjunction is false is when both its parts are false, okay? So this is the one rule to help you memorize the truth function of the disjunction wedge operator, okay? Now here we have the statement, today is Monday, and then we have the statement, it is raining outside. And then we have the disjunction, today is Monday or it is raining outside. Now if today is Monday is true, and it is raining outside is true, then today is Monday or it's raining outside will also be true, okay? However, this will also be true if one of these is true and one of them is false. Notice, if P is true and Q is false, the statement is also true. And if P is false and Q is true, the statement is also true. Okay? So the only time this statement will be false is if it's false that today is Monday, and if it's false that it's raining outside. Okay? Now, if you think about it, the disjunction actually makes sense in a specific understanding of the disjunction operator. Okay? So let me give you an ordinary language example. So in ordinary language, we think of the disjunction, the logical operator, which is the wedge, as associated with the word or. Okay? So if I give you the statement, you have apples or you have oranges, when is that statement true? Okay? It's true if you have apples and you don't have oranges, right? So it's true if you have apples and you don't have oranges, okay? It's also true if you have oranges but you don't have apples, okay? So it's also true if you have oranges but you don't have apples, okay? However, it is also true in propositional logic if you have both apples and oranges, okay? So if you have both apples and oranges, then that statement, you have apples or oranges, will be true. The reason for this is because, and I mentioned this in previous lessons, we use what is referred to as the inclusive disjunction in propositional logic. Whereas normally in ordinary language, like when you go to restaurants and stuff, you only use the exclusive disjunction. So in this case, because of the inclusive disjunction being used, this disjunction is going to be true if P and Q are both true. Okay? Finally, you have apples or oranges is going to be false if you neither have apples or oranges. Okay? So the statement, if you have apples or oranges, will be false if both of the disjuncts are false. Okay? Next, we have the conditional operator, okay? And this is the truth table, which illustrates the truth function of the conditional horseshoe operator, okay? Notice how it suggests that when P and Q, which are the parts of the conditional statement, P being the antecedent and Q being the consequent, okay? So if P and Q are both true, then the conditional statement will be true, okay? If P is true and Q is false, then the conditional statement will be false. If P is false and Q is true, then the conditional statement will be true. And if P is false and Q is false, then the conditional statement will be true, okay? The one simple rule to use in order to memorize the truth function for the conditional horseshoe is the conditional statement is only false when the antecedent is true and the consequent is false, okay? So notice how this is the only occasion when you have the antecedent, which is P, taking this first position, being true, and the consequent, which is Q, taking this last position here, which is false, will give you a false conditional statement. In all other cases, you will have a true conditional statement. Now, if you think about this in ordinary language, it might be kind of odd to you, right? So if I give you the conditional statement, if Socrates is human, then he is mortal, okay? According to the truth function of this logical operator, the statement, if Socrates is human, then he is mortal, will be true if it's true that Socrates is human and it's true that he's mortal. It'll also be true if it's false that Socrates is human, but it's true that Socrates is mortal. And it'll also be true if it's false that Socrates is human and it's false that Socrates is mortal. Okay? However, the only time it'll be false is if it's true that Socrates is human and it's false that Socrates is mortal. Now, it might make sense to you that, okay, when both the P and the Q are true, if Socrates is human and Socrates is mortal, then the statement, if Socrates is human, then Socrates is mortal, would be true. That seems to make sense, right? However, you might be confused about these two truth values here. Why is it the case that if it's false that Socrates is human, but it's true that Socrates is mortal, the conditional statement is still true? Or if it's false that Socrates is human and it's false that Socrates is mortal, the conditional statement is true. This is quite odd. Now, one way to understand this a little bit better is to think of the conditional statement as a hypothesis in science, okay? So consider this. If I give you the conditional statement, if I drop this clicker on the floor, then it will fall, okay? How would we know that it is false, okay? As a hypothesis, we would know that this hypothesis is false if we drop the clicker on the floor. So if it's true that we drop the clicker on the floor, but it does not break, okay? So the statement, if I drop the clicker on the floor, then it will break, will be false. If I drop the clicker on the floor, the antecedent is true, but the consequent is false. The clicker doesn't break. Now, we know that it'll be true that if I drop the clicker on this floor, the clicker will break if I do indeed drop the clicker on the floor and it's true that it doesn't break. So if the antecedent and the consequent are both true, we know that it's true that if I drop the clicker on the floor, then the clicker will break. However, consider this. If the conditional statement is a hypothesis, if I drop the clicker on the floor, then the clicker will break is a hypothesis. I'm not testing this hypothesis if I don't drop the clicker on the floor, right? If the antecedent is false, you're not testing the hypothesis. So, because we're not testing the hypothesis, okay, it doesn't really matter. So here we're not testing the hypothesis, and here we're not testing the hypothesis. We're not dropping the clicker on the floor. It doesn't matter if the clicker does break or if the clicker doesn't break, okay? If the consequent in these cases will be true or false, it's still going to be a true statement because we're going to assume that the hypothesis is true unless it is proven false, okay? So think of the conditional statement kind of like as a hypothesis in the science. We're going to assume that they're true, okay, unless we're going to be able to prove that it's false. Okay, so this is the one rule that will help you memorize the truth function of the logical operator, which is the horseshoe. Okay, the only time a conditional statement which uses the horseshoe is false is when the antecedent is true and the consequent is false. Okay, so here we have example of statements in ordinary language and then translated into propositional logic. We have T being the statement, today is Monday, R being the statement, it is raining outside, and then we have the conditional statement, if today is Monday, then it is raining outside, okay? So this statement is going to be true if it's true that today is Monday and it's true that it is raining outside, okay? So if today is Monday, then it's raining outside will be true if both of its parts, okay, are true, okay, which is given right here. So if P is true, this is P, and Q is true, this is Q, then the conditional statement will be true, okay? However, if it's the case that today is Monday, so today is Monday is true, but it's false that it is raining outside. So it is raining outside, okay, is false, okay? You will have a false conditional statement. So this will be false. It will be false that if today is Monday, then it is raining outside. Okay? And if today is Monday is false, okay? So today is Monday is false, T, okay, which takes this antecedent position, okay? So if T is false and R, it is raining outside, is true, okay? Then this conditional statement will be true, okay? And if it's false that today is Monday and it is false that it is raining outside, then the conditional statement will again still be true. Why? Because we're going to assume that the conditional statement is true like a hypothesis in the sciences until it is proven false, okay? And because in these two cases, when the antecedent is false, we're not testing the hypothesis to prove it false. We're going to simply accept that it's going to be true until we can prove it false, okay? Our final logical operator is going to be the biconditional triple bar, okay? And this is the truth table, which shows the truth function for the triple bar operator, okay? So according to this truth table, which shows you the truth functions, a biconditional statement that uses a triple bar as its logical operator will have the following truth values given the truth values of its component parts, okay? If P is true and Q is true, then the biconditional will be true, okay? If P is true and Q is false, then the biconditional will be false, okay? If P is false and Q is true, then the biconditional will be false. And if P is false and Q is false, then the biconditional will be true, okay? So the one rule that you can use to help you memorize the truth function for the biconditional logical operator is the following. A biconditional statement is going to be true anytime both the statements that make up the biconditional have the same truth value. So notice here, when P and Q have the same truth value, they're both true, or they're both false, then the biconditional will be true, okay? And in all other cases, which is when they have the opposite truth values, okay, the biconditional will be false, okay? So you can use that one rule in order to remember the truth function for the biconditional operator, which is the triple bar, okay? So here we have three statements in propositional logic as well as ordinary language. We have T standing in for the statement, today is Monday, and R standing in for the statement, it is raining outside. And then we have the statement T triple bar R, which stands in for the statement, today is Monday if and only if it is raining outside, okay? Now, it's gonna be true that today is Monday if and only if it's raining outside. If it's true that today is Monday and it's true that it is raining outside, or it's false that today is Monday and it's false that today is raining outside. In any other case, if it's true that it's raining Monday and it's false that it's raining outside, or it's false that today is Monday and it's true that it's raining outside, the biconditional triple bar will be false, okay? So when you have the parts that make them up have opposite truth values, the biconditional, okay, will be false. The reason for this is because what the biconditional is saying is that P is logically equivalent to Q, meaning it's saying, the biconditional statement, that P means the same thing as Q. So if P means the same thing as Q, okay, and the meaning of these statements are their truth values, then the statement that P means the same thing as Q is going to be false when they have different meanings. So P means the same thing as Q is going to be false when they have different meanings, okay? But P means the same thing as Q is going to be true when they have the same meanings.